researchers. Okay, to begin with our talk, we have a very interesting video from Professor Figueredo, so let's watch it together. 还有话筒吗？给嘉宾一个话筒，对。Yeah. Okay. So, Luis, could you also briefly introduce what's the scenario of this experiment?
Yes, absolutely. So this was I work at 3 a.m. 2 days before ICRA deadline, 2022, if I'm not mistaken. And 3 a.m. I was in my office working, and the students got me in my lab. It's working, let's see. And they were so excited to show the family that was working and to get the professor drunk as well. And they were trying to show, man. It was obviously not working. The paper survived though. It worked later. It's published. The students are alive. Some of them are here. It's good. Research. It's research. It's research. Yes.
So, did your students mess up the foundation model edition of the
I would say
experiment?
mess up. It happens. Yeah. So it's the idea here was. It's learning by demonstration with one shot. So basically demonstrating once and deploying immediately in a new scenario where there is obstacles, where there is obstruction. So the student was trying to be in front of the robot, the path. So the robot would have to go away from the person. But this was mostly focused on geometric methods that then we would embed the foundational models, we embed the natural language processing, the visual large language models. And over there, clearly there was none. So they didn't know where to position where to pour the cup, and naturally they pour on me. But these, as follow-ups, and you'll see in the other videos, we integrate natural language processing, visual large language models that we could use. For instance, while it was pouring on me, I couldn't just tell, well, stop pouring on me, and the robot would understand and would retract throughout the trajectory. So it's mostly about how you translate this high-level command, this high-level interaction into low-level control methods, low-level motions from the robot.
Okay, I see. So later on, how did you solve this problem? Did you collect more demonstration samples?
Not more demonstrations, because here the idea is exactly to demonstrate once, and the robot, less than 1 second later, is able to replicate that in a different scenario. We are executing that with a team in New York, and they are executing by manual robot the same demonstration that we did here immediately. So the idea is that industry could use that immediately. But to generalize better, to generalize different scenarios, then we use foundational models so we can understand what is the scene, and you can replicate in different scenes. And different demonstrations, you can also understand what the scene we have, the semantics of the scene. That's and the error we fix with the other video where we have the interaction of the person talking to the robot, and the robot understands, okay, you should not do that. So it's more for reshape of trajectories, failure recover, online, real time. So that's how we fix it.
Yeah. So there's also a follow-up video from Luis. Let's watch that together. Does it have anything to do with coffee? So that's why you call it a latte?
It was a breakfast. So roughly coffee. You want to demonstrate a breakfast scene where the robot was trying to kill me. So it was worse than the beer, I guess. And I could tell the robot, well, get away from me, please, or go slower if you're trying to kill me. And the robot would understand the intensity of my conversation. If I tell, get away from the laptop, because I don't want you also to destroy my laptop, just go away from the laptop. And the robot would reshape the trajectory on real time.
So before trying with the knife, have you considered any other safer tools?
We consider other safer tools. Here, for instance, it's just liquid transportation. So there, I wouldn't mind get water again, but I wouldn't like it on my laptop. So that was what I was afraid of. So the command was to get away from the laptop. But this could be generalized for anything, of course. And in terms of the knife, the other part is that we also ground in some terms of safety. So I have like a safety controller that controls the velocity of the robot as it gets closer to me. So there is a whole embedding of grounding that the natural language processor goes through the system before being deployed in the robot.
So later on, did your students also try with this knife experiments?
With me, no, that students I would allow. This is another student.
Okay, so you are the first one to try with this knife.
Yes, I was the test.
Yeah, me too. I think when I was a PhD student, I also did run experiments with myself first. If it's safe, I would invite other participants.
Yeah, but they do on me.
So you also mentioned foundation models. So usually at what stage did you use foundation models in your robotic system for perception or for language interaction?
So both. It's not limited in terms of the interaction. The interaction is very clear. It needs to be there. But of course, for perception as well. For generalization of tasks, once you learn once, you can generalize. But the main point is that when you're doing manipulation tasks, when you're doing contact reach manipulation, when you're doing safety risk manipulation like that, it's how you embedded the system, how you embedded the foundational models, how you use it in the manipulation tasks. So you really need to think about the embedment on the grounding, understanding the features that you have. So first you generalize having a better feature space, not trying to understand the whole world, but understanding what is relevant. In the second stage, what could be risk assessment, what could be dangerous, and what exactly you want to do, and grounding that in the manipulation task. So it's a really a combination of model-based, model-free approach, so we can really have a robot deploy in the real world easily. Risk assessment, what could be
any questions
what could be dangerous,
from our audience?
and what exactly you want to do, and grounding that in the manipulation.
So, yeah, okay. So my question is that since I think that between this demo and the KMP or the imitation learning, they can also do this trajectory planning. So I think that maybe your demo is different to this imitation learning mechanism because I'm not sure whether I'm right.
Yeah.
So you use your model to identify the dangers automatically, not by the imitation learning to avoid the obstacle by setting by manually. Is that correct?
So you're asking if we pre-train the... No, you're right. So we have the trajectory plan only once, and grounding in the semantics relationship between the object that we have, grounding the geometric transformations from what you have. That's how we do it. Just
so we don't need to tell the algorithm that here you should avoid, and it can know that I should avoid this automatically by the fundamental model.
You can do that, but here the idea was exactly to reshape online. So the idea was that you have an initial trajectory that was going to be dangerous, that was going to be risky, or if your perception model fail, it's going to go through to the cup, and it is able to react on the time and please go to the left or please avoid the cup, and react on real time. The main thing is that the reaction needs to be on real time. It needs to be under the constraints of the robot. So it's
Thank you. Thank you.
So it's a mix.
Questions? Any other questions?
I have a question that is more a curiosity. So when you deal with this large language model, now to somehow describe the action, I think that there is a great variability on how the user describe the scene. So do you think that in the future, so people will be more used to do this, and this will be improved, or do you think that will be always hard to describe a scene for a robot?
That's a very good question. maybe we understand better once you have more interaction with the robot. We are very good on adapting ourselves, right? So if we start using and we start adapting, then we will be able to hack the system very easily. So you're going to be able to understand, okay, this is how I should communicate to get what I want. So I think there will be this really bilateral interface where the system learns, but the person also learns the system. Will probably learn faster, but yeah. Right now.
Is there an interaction between the conversation? Like the robot will say, "I will not be able to do that," and then please send me a different way, another constraint, like etc.
Yeah. So this is not in this one. This is exactly what we're working now. So you're working dialogue, extending that. So in this version, we could have some dialogue, but it was mostly like interacting, like iterative approach. And now we are working more in the dialogue space. So you could have like even the preference. That's a good question.
Thank you, Luis. And Professor Martin, I know you have a work with Professor Feifei Li tackling the long horizon mobile manipulation via factorized transfer learning. And also in your video, there's also a segment that the robot can pour the water. So let's have a look at that together. Yeah, it was successful in the video. So have you also encountered any challenges for the robot when pouring the water?
Sure. The problem here is that it needs to learn. This was using reinforcement learning, so it requires a lot of data. And the problem is also for mobile manipulation, you need to control a lot of degrees of freedom, and it's very complicated and noisy. That's why we use some form of causality to simplify the signal. But one of the good things of foundation models, if you use them as generators of actions, is that you can start with a much better starting point instead of having to learn tabula rasa every time from scratch, like we were doing before in reinforcement learning. So it's going to be more efficient than what we had to do here. But yeah, here the robot is coordinating the base, the arm, and the head to not lose track of where it has to go. Even if there are distractors in the scene, it can compensate for that. So that was the challenge here, coordinating all these degrees of freedom from the mobile manipulator.
Okay, I see. So later on, there is also a video. We can see that the robot can clean the kitchen in the real world.
There's the mystery.
Yeah. Technical issues.
The next one. Yeah, this one.
Oh, there we go.
Just suspense.
I see that you give it the name member. So
Yeah.
can this robot become a family member in the future?
That's right. So the fun thing here is that everything that the robot learns in simulation. And I've been doing a lot of research in simulation together with Feifei and my lab because it's fast, it's safe, and yeah, it's basically a very good environment. It's like a playground for the robots to learn to do these things. The problem always is how do you transfer that to the real world? So that is what we were focusing here on, how to transfer what the robot learns in simulation to the real world, even if the real world is different to the simulator. So yeah, basically what we were doing here is to factorize the different skills that the robot needs to learn, and that is the interface to transfer what it learns in simulation into the real world. Again, here we were using some form of reinforcement learning. but with these factorized skills becomes more efficient to transfer to the real world. And these are all kitchens that the robot has never seen and is able to coordinate everything and clean the cupboards in all these new kitchens for the robot. So yeah, that was, we were very, very surprised with the results here. And yeah, we were very, very happy. So yeah, this was amazing work by Bohan, and was nominated for an award last ICRA. And really, yeah, became a member of the family, the cleaning member of the family.
It looks like it's a very big smart home. So it has a kitchen, maybe it also has bedrooms, so that other researchers can use this place for robot navigation. Do you use for that kind of experiments?
This one?
Yes.
This was at Stanford, different kitchens at different levels of the building, of the Gates building. We also had some, we built our own fake apartment in the basement to do tests. But what I would like to do next is to bring the robot to real apartments. And because always these environments are slightly different to a real apartment. Real apartments are more messy. We leave things around, and we're a bit more kind of like chaotic than what you find in a fake environment. So going into the wild is the real test for all these solutions. And that is what we should do more in academia, going into the wild and really test and see what happens.
I see. So did you utilize any foundation models in this work?
Not in this work. Again, this was a reinforcement learning project, and we didn't start with a foundation model. But the same as with the previous project, the next ideas in my lab is to not have to start learning everything from scratch, but foundation models give you a very good starting point. So in my lab, we try to use foundation models in two ways, either as common sense generators, which is more like what Luis was showing. It's a knife, I don't want it close. So that knowledge is already encoded in foundation models, or as action generators, just the architecture of foundation models to consume images and other signals and output actions for a robot. So these are the two ways we are exploring in my lab to use foundation models, either create our own action generator foundation models or use common sense foundation models like LLMs and VLMs.
I see. Any questions from our guests?
Yeah, I have a question about the perception system for this robot. So are you using only onboard sensors, or there is cameras in the kitchen?
Yeah. So for both, we are using just the onboard sensors. That is very important for mobile manipulators because it's one of the big challenges. When you have a robot that navigates, you cannot assume that the robot is gonna see everything that it needs to see. If it just rotates, it's gonna forget what is in there. So that is a big challenge in mobile manipulation. This was all with cameras on board. There was no external cameras. The previous video as well is all the cameras that the robot has on board, and it needs to use actively its degrees of freedom to point the cameras to the right locations, which is a really big challenge.
Yeah, so dear guest, when you use the microphone, so you can hold it in this way so that our voice can be more louder.
Okay, sure.
Yeah, okay. So any more questions?
Oh, good. Since we are supported by NOKOV, I would like to make an advertisement. you can try reel to reel if you have NOKOV. Thanks. Okay, let's.
Yes, of course. If I get a donation, I will try that.
Let's get back to the topic. Well, from my experience, if you have a mobile manipulation,
yep,
you have lots of scratch on the surface of the refrigerator or the cleaner. I see it's a fully reflective. Does that mean you have a very good performance from the sim to real, or do you have some failures in the experiments? And you don't have scratch there. I mean.
Yeah. So we always work with compliance controllers so that we are as gentle as possible when we contact the environment. But yeah, that's a risk. Robots are hard, and in some other line of research, we're looking into how to create manipulators that are softer and can get into contact without breaking things, and adding that to controllers that are also adaptive and kind of like control the amount of force. I think that is one of the challenges in robotics right now. Move from kind of like pick and place to really contact-rich manipulation is a challenge for any robot. So yeah, here we were very careful, but yeah, there were some scratches that you cannot see in the video.
That means you have the model-based control after the learning.
Yes, learning is an interface, sends commands, and then we have a model-based controller that adapts impedance to be more gentle with environment.
That sounds reasonable. Thank you.
Thank you. Any other questions? Okay, then let's move on to the next video. It's from Professor Gaofeng Li from Zhejiang University. So Professor Li, I know in your recent work, you and your team developed an agile telerobotic system, and you did various experiments in disaster response scenarios, especially after earthquake. So let's watch this together. So while we show the video, could you also briefly introduce the motivation of this work?
So here is the story. Is that the background is that after earthquake. Not open. Okay. So here is the story background. Is that after an earthquake, we think that in our lab there is a gas leak. So we have to send our robots to enter the lab to handle this case. And so to do this, we have to do first open the door, and then since it's not a normal lab environment, so there is some obstacles that to stop you to enter the place. So we need to clear the obstacle, and then we will use our bimanual manipulator and bimanual hand to do the wave turning tasks to close, turn off the leak, the gas, and since this is a lab, and we will also have very important data here. So later, and we will plug in the USB drive into a computer and get the important data, and then get a plugin outage, and then we will also have some samples that is very important. But since after so many complex manipulations and so many complex tasks, and there is still little time left to the robot. So our robot have to move first, and at the same time, it have to grasp the sample and would go out the lab quickly. So this is what we are doing, and want to tell a story about this case, this scenery. And during this scenery, and what's the problem is that so we want to build an agile telerobotic system. So when you mentioned agile, it doesn't only mean low latency. It means that you have to correctly human intention cognition. You have to understand what the human wanted to do. And then the field robotics or the remote robotics have to respond first quickly, such that it can follow your commands. And also, we should have very exact sensing about the environment, such that human can understanding what is happening in the remote environment. So for our system, this is a very close collaboration between the human and the robotics. And to do this, you have to have exact cognition of human and the first response in the leader side, in the follower side, and also accurate sensing. So to do this, especially for your hand, so you for your manipulator in such a huge space, you have only 6 or 7 degree freedom. But for your hand, in such a limited space, we have at least 20 or 24 degrees freedom. So the problem is that how can you sense humans' motions? This is what we did. And also in the remote side, the tactile sensing is very important, but this is still a bottleneck for our current. So we are doing this. Okay.
I see. So for the robot to detect the environment, what kind of sensors are equipped with the robots? For example, RGBD cameras or other sensors?
So currently, and for the whole picture, and we hope that we will have some global or multiple views of cameras, and so to give the visual feedback about your remote environment. And also when you do manipulation, but it is still not added in this case because it is just a demo. And so, but in the real case, we will install in camera at the end effector of the arm, so that it can observe what is happening, give you the visual feedback, and also between the hand and the manipulator, we will have the FT sensor, force and torque sensor, to give you feedback whether I'm touching a wall and whether I have grasped the end object. We will give you the weight of the object, and also in your tip, the fingertip, we will also have tactile sensor, but not in this this demo. And we are doing the design and fabricate a new human-like tactile sensors. And in the future, we hope to show you more demos.
Thank you. So is there any shared control in your system, or the decision is completely made by the human teleoperator?
Okay, this is a good question. In this demo, and it's fully controlled by the human manipulator. Actually, the high level is fully controlled by the human because it can do decisions. But for the low level part, for example, the control of the manipulator and the movement of the mobile platform, the quadruped robot, and it is done automatically by the robot. It's low level intelligence. So actually, we have a survey paper and published in Transactions on Haptics. The title is that the classifications and nutrients for the shared control strategies, a survey. So I recommend my paper to you guys and to refer to that. Actually, we have mentioned that there are two nutrients in shared control. Is that the first thing is that we hope that the autonomy can be learned automatically by from learning, and because and the kinds of for autonomy it is very difficult or tedious to encode by manually. So we should do it automatically and from learning. And the second is that the human level, the autonomy level should be adapted seamlessly, because and according to different operators and different tasks, you should use different level of autonomy. So here is the case is two different ways. That one way is that to do the change and adaptation by human, and the second is that we hope, but this is is the first step. And we think the first step is that we hope the system can do this adapting according to the environment information and also according to the human's feedback, and to do the adaptation automatically. So we think this is the future. And no matter what's the intelligence of the robot do, and we think that the robot always should be controlled by our humans. We do not want to be a robot that can ruin our human society, right? So no matter any level of the robotics, we hope it's controlled by humans. But at which level and should have what kind of autonomy level the robot should have? We hope that it can identify or judge according to the environment, the sensings. But this is still the open problem, and we hope we can all work on this. Thank you.
Thank you. Yeah. Any other questions from our guests?
So you talk about the shared autonomy, and it's always curious. I was curious first on what kind of haptic device you had to control the system in this application, and if your ideal scenario, what kind of, for this application, of course it's dependent on application, but for this application, what is the level and what is the interface for the shared autonomy there?
Okay, so in this scenario, and to capture humans' intentions, we have the device. For example, we have omega 7, which is used to capture the left hand motion, and also we have the grip degree, such that it can control. As you can see, that our the two arms, one is equipped with a gripper, and another one is equipped with a dexterous hand. So for the left hand, we use a gripper omega 7 to capture motion and give force feedback. And for the right hand, we will have a hand skeleton developed by ourselves, and also another haptic device also developed by ourselves, and also we will use this device to capture the whole motion of the hand, also the fingers motion of human hands. So we use this device to capture the intentions of the human. And as you know, this currently is only the motion intention. And in the future, we will also include other, for example, the EEG signals, and that is future story. And in this video, the second question is about the shared autonomy. Here is that we use we call it the semi-autonomous shared control. In this way, and the human controls some states that the autonomous control controls the other states. In this level, and the states are into different levels. So the robot autonomous controller, it will control some low level, for example, the joint angles, such that it can achieve what you want to do. And the human will give you the Cartesian position, and also in the future we will have the soft the compliance control. So it gives you the high level commands, and for the low level stuff, that we will give the robot to do the control and the model-based control automatically. Yes, thank you.
If no more questions, then let's move to the video from Professor Weiwei Wan. So Professor Wan,
Yes.
could you briefly introduce the background and motivation of this research work?
Sure. In this video, the robot is dripping different chemicals to the plant, and essentially we are screening these chemicals. We are looking for the plant that has a genome type that is highly resistive to dry environment. While we are applying the liquid to the chemicals to different parts of the plant, and as you can see, some of them are applied to the leaves, and some others are to the earth, and others are to the stem. While the robot has two cameras and the effector. The robot used the two cameras to detect the leaves, the stems, and the earth. And also, you can see in this process, the robot is picking a tip. That is a conventional pegging hole task in robotics. And the difficulty is these tips are not fixed. The robot cannot use force control to attach them. We are also using vision. Also, they are small. You will not be able to detect them one by one independently. We use a transformer, vision transformer, to estimate the offset between the shaft of the tool. The name of that tool is called the pipette. We use a transformer to evaluate the offset of the shaft of the tool from the center of the pipette, and then it's like a one-shot assembly insertion, and pick up the tip and then apply the liquid to these different parts of the plants. And you know, all of the leaves were green. It's difficult to separate each of them. There was a challenge called, well, I think Martin is familiar with this. This was a challenge called the leaf segmentation challenge in plant research. And the goal was to separate each of the leaves using a neural network. And we borrowed this neural network to separate them. That's all about this system.
So you mean here you need to segment each piece of the leaves, and will there be any blurries in the boundary of the leaves so that it can cause some segmentation failures?
Definitely. But it's a neural network-based result. If there's some uncertainty in the boundaries, well, you can increase the data sim to real, well, various technologies, but we don't know why. That's the only problem here.
So is it a long-term experiments in the lab after, so you would observe how the leaves would grow after 5 days or 1 week?
Yes, that's a good question. We developed this system for the scientists, for the plant scientists. And the robot will run for all of the 120 pots of the plant. You know, I'm in the technical committee for mobile manipulation together with Martin. And I was considering where is the mobility here. And you see the pods are moving to the robots. That's tricky, I know. There are 120 pods here, and the robot will apply the 3 different, I guess six different kinds of liquids to different parts of the plants. And we will receive a list of the data after 5 days. And we will send the data to the plant researchers, and they will identify which liquid is better for this kind of applications.
Yeah. Interesting work. Any questions from the audience?
So I'm wondering, do you also analyze the results with computer vision of what is happening to the plant? Do you analyze if the leaves are greener or browner, or do you also close the loop on that?
That's I guess, an question. We were working on that. Well, but the training data is difficult, especially when the plant gets dried. The color is the same as us. It's brown, and we have to ask humans to crop out the boundary and then feed them to the neural network. That's the difficulty.
Yeah, it's a complicated perceptual task, but then you could have the robot do everything. Try and see the result and try again and learn what is happening and, I don't know, explore itself.
Automatic experiments. That's the dream of all of the scientists in bioresearch. And they hope to only design the protocols. The protocol means how the experiments will be performed, and then get the data to know the results.
The dream of scientists and gardeners, I guess.
Just as a follow-up, and yeah, I would love to have that because I'll kill my plants. But could you think that you could use the manipulator to, instead of asking people to segment where it is, but having different views on the camera, perhaps like a sensor placement, where would it be better to have like the shadows? If you look on the side, you would look the volume of the plant, perhaps something like even tactile, perhaps, so you would avoid the human side of it.
Yes. Well, this is called the next best view estimation for the cameras. We also have some works on that. But in this case, the camera is fixed. The reason is these are 2 separate systems. And for this, previously, this system is called the LIPS system. It's the Liken prolonged phototyping system. It's called LIPS. And there was no manipulators in the LIPS system. And the pods are rotating in this flat surface, and then a human research scientist will apply the liquid. And there's a time limitation for each step. And we don't have much time. We install this new manipulator, but there's not much time to do the next best view. That's the reason there is one shot, everything is one shot.
So we have talked about the challenge about the perception of this task. So my question is about another level is that about the manipulation. is that it's not easy to do the packing hole or absorb drops from liquid drops. So could you tell us and or share some challenge in this part? And what kind of sensors you have it? For example, have you used the tactile sensor and to finish this job?
Thanks. There's no other sensors. Everything is vision based. We have those two cameras, and one particular interest might be we had two cameras there, and we used the 2D images and we send them to the neural network. We found that two images are better than the single one. It's probably the neural network is learning the 3D reconstruction from these two images. That's the only thing we think we are particularly interested in robotic vision. And tactile sensing, it's definitely another interesting point. But installing the sensor might be challenging. Well, the system is compact. You have to design where and how and the shape of these sensors. That's it.
Thank you. Questions?
Okay, thank you. So do you still work on this research work, or is there any further plans for it?
Thanks. That's an excellent question. The next one is probably diffusion model and generative motion. Well, the next one is they want to keep a sample of these leaves, and you can see that the leaves are cute. They are small and they have fresh green color. And the goal is to use a scissor to cut a piece of the leaf and then save it to liquid nitrogen. Well, cutting the leaf, you have to detect those thin stems. It's pretty difficult. I don't have a good solution, but right now I'm considering the diffusion model. It's difficult to be detected by depth sensor or pure vision. I don't know. We are still looking into it.
Thank you. It looks like it's very delicate manipulation because you know the very tiny difference between the depths of leaves. Yeah, very challenging. Yeah. Okay, thank you for sharing. And let's watch the video from Professor Salvietti together. So could you also briefly introduce the background and motivation?
So here there is a design of a novel gripper to handle fabric, because we were studying this problem of helping people to dress, and usually, I mean, it's difficult to design the correct gripper to use it, because if you have a very stiff gripper, then you have to be extremely careful, because when you are in contact with persons, so you have to design to accurately design the trajectories, and you have to I mean, if you are doing learning, you need to acquire a lot of data. So the idea here is to design a soft gripper that can basically have a safe interaction with the I mean, in this case, with the patient. The point is that if you design a soft gripper and you make finger soft, then it's really hard to apply a high force to do a pinch grasp. Usually, soft grippers are very good in doing some enveloping grasping or some force grasp. They are not very good in doing pinch grasps. So the idea here was to make this soft finger, but then add electromagnets on the fingertip. Then basically when you grasp the fabric, when you grasp the skirt, when you grasp something, then you activate the electrogripper, and then you have a very strong pinch grasp, and then you can do this. And actually, the idea, so this is something that can help to apply higher forces when you do the dressing. But then go back to what Roberto was saying before, then adding some compliance in the system, it's really important. it's something that, I mean, from the learning point of view, we always want very nice labeled data. So we want everything to be super rigid because we can replicate it. While with softness, it's really hard to replicate because every time that you do something, I mean, it's hard to model and also hard to do to reproduce. But actually, adding softness and adding compliance in the system for this kind of strict interaction with people, actually we low down the complexity because your system could be less precise because there is compliance in between, and then somehow is a kind of embodied intelligence on the gripper that cover for the less precision of your system. So we start to design this kind of gripper actually to explore this possibility to reduce the complexity of the control and somehow move it to, I mean, complexity is there. So we are all dealing with very complex problems. But most of the work I see on learning in general, they always use very stiff things because of this problem of labeling and getting data, while probably a more bit, so putting a bit of intelligence in the tool would help to reduce this complexity. So we want to explore this.
Yeah, I see. So you concern the safety and also the comfortability of the user. So it is quite user-friendly. Have you also tried some tactile sensors with the robot fingers and try to grace?
Yeah, this is a very good point because it's another problem when you have soft tractor is to sensorize it. Maybe later on Martina will tell us something because of course it's complex to add reliable sensors. We are doing some work now adding different sensors in the compliant part to try to estimate it. We do not have a proper tactile sensor at the moment there. Especially in this application, actually we have no sensors on the gripper. We are estimating the interaction force directly from a sensor in the wrist of the robot. So then we do not have anything on board, but for sure this is something important to consider. Yeah.
Thank you. Any other questions from the guests?
So you mentioned adding intelligence to the embodiment, and yeah, I think that is a great point. There is kind of like this spectrum of computation and embodiment, and where do you place yourself? I guess one of the problems of having the computation on the embodiment is that you may lose generalization. So how is the case for this gripper? Is a gripper that is general, you can use also for manipulation, or is very specific for this task and is rather difficult to generalize to other tasks? How was this trade-off?
Yeah, this is a very good point. To me, this gripper is a very general gripper. You may use, I mean, this is a specific add-on, let's say, with electromagnets that are related to the manipulation of fabric, but we have same collaborative gripper with the same structure of the gripper that you can use for many collaborative, classic, let's say, collaborative robotics, but we are also using for assistive tasks where you interact with patients and that's it. So I may say that this is really general. Then I think that this kind of compliance actually may help in generalize because you have something that can, so for instance, let's pick the example of the classic grasping problem, no? So if you have something that is really stiff, you have to plan exactly the location of your contact points, right? So if you change the object, then you have to plan again for the new object. If you have a soft end, basically you don't plan for the contact point. You simply go there and then you close, and the end automatically adapts to the object you had. So if you change object, there's no problem. The end can adapt. Of course, then it's difficult to do fine manipulation of these things. So if your task requires some skill that is not easily manageable with these soft grippers, then you need to add something. But if it's, the task can be generalized, then this embodied intelligence to me helps in reducing the complexity of the system.
You said that you were adding first sensors to get the information. Were you doing any calibration before? Because of the transformation, you get the loss of energy because of the softness when you're using it, how the calibration process was.
Actually, yeah, we did some calibration to test the forces that can be exerted, but actually it was nothing. I mean, if I remember the experiments, there was nothing too stressful. We simply got there and we set some maximum force that you want to extend, and then there is the controller of the robot that runs below that basically try to not extend this high force. And then we have a kind of predefined trajectory, and we change this trajectory according to the maximum force that you set. So yeah, you need it. And I mean, you also need, of course, when you change, if you have some complex gripper and you plug in onto the system, you need to calibrate everything because to consider the weight of the gripper. But then once you did it, it's pretty straightforward.
Thank you. Actually, during my PhD at Imperial College London, my research topic was also on assistive dressing. So the next, I would also like to share with you some of my demo videos. So this work was done in 2015, and it was published in ICRA's 2015. So at the beginning, we worked on the user modeling of a human using the vision information. So I collected the movements of the user's upper body, and we modeled the movement space of each upper body joint using Gaussian mixture models so that the robot can learn the preferred action space of the user. And in the experiment, together with the real-time user pose recognition, the robot designed the personalized dressing path for the user. So this was the first edition of my experiment. We used a sleeveless jacket, and that girl, she was my friend. At that time, she was also doing her PhD at Imperial College London. So I was on the 10th floor and she was on the 11th floor. Now she is also a professor in a university in the UK. Yeah, so that was the old work. And later on, after I joined Jilin University, I also built my own lab. So we worked on close grasping and unfolding because we can see that the robot needs to detect the grasping point and unfold it to a state so that it can be easily so then it can help the human to dress the clothes. So we use the RGBD camera. We do the grasping point detection. So yeah, here I would also like to advertise a little bit of our sponsor, NOKOV Motion Capture. So when I joined Jilin University, I'm also kindly supported by the School of Artificial Intelligence. So the school supported me with this robotic lab. And because at Imperial College, we have this motion capture system in the lab. So when I joined in the school, I also asked the school if they can support me. So they asked me to search by myself, to decide by myself. At that time, I searched on the internet. It was in 2021. I didn't ask anybody else, but I chose NOKOV directly, and I think it's the rightest decision I have ever made. So to detect the grasping point, at the beginning with the motion capture system, I put markers on the shoulder part of the clothes. So we use this as the ground truth grasping position for the robot grippers. And we collected both real world data. So actually it is depth images with the grasping point positions. Meanwhile, we also collected some simulated depth images with the physics engine Maya, so to also generate a large amount of simulated depth images. So together we train the neural network, and we enable the robot to autonomously detect the grasping point. So that's the work. And also later on, we also designed our own segmentation system. So we use both RGB image and depth image. So to segment each part of the clothes, so we divide it into the outer side of the coat and also both the inner side of the coat. So after detecting the graspable areas, then we also design a grasping point chosen mechanism so that the robot can find the most appropriate grasping point. So that's the story. And later on, I also tried this interesting assistive dressing experiments with my student. That was my first master student at Jilin University. So because our motivation is to enable the robot to grasp the clothes and fold it to a state. So later on, we also tried this to help with a real human user to dress the jacket. Yeah, so that's the story. So that's why when I saw that video, it also reminded me of my own story, both as a student at Imperial College London and later on as also associate professor at Jilin University. Yeah, I thought maybe I read that paper, this soft gripper. Yeah, I think during the background study. Yeah, so nice to meet you. See you here. Okay, and actually just now you also mentioned these soft sensors. So we also have our guest, Professor Martina Maselli. I know that you worked on soft sensors. So could you also briefly introduce your research background?
Yes, I can talk about my research topic. That is the study improvement of soft sensor. Okay, for different applications, based from the agri-robotics, but to wearable also device and biomedical application. I started my research career by developing a soft sensor as wearable sensor to monitor joint angle, but also for some pressure detection. And I moved also to different type of application, and I worked and I'm working on different research projects in which the objective is the implementation of sensitization system into soft robots. Since the main challenges, as always explained by Gionata, for soft robots is the sensorization and the control of the soft robot. So my research focus is the implementation of the sensorization to integrate the proprioception and also the exteroception for the robot and improve the control of the robot. And I'm also working on different research projects in which the objective is also always the development of sensitization system, but for different application. And for example, now we are working on a project in which the aim is the development of a soft gripper for agriculture field, and in which we should also develop the sensitization system to improve the projection of the soft robot, but also for a wearable device as assist garment for elderly people or impaired people.
So would there be some noises for this kind of soft sensors? So how do you deal with the noise, the detection, the noise signal? Yeah.
Yes, but in the soft sensor that generally I developed, I don't have much noise since it's based on a piezoresistive detective principle, mainly for strain and pressure detection, and there is a noise, but I always cancel the noise by applying a simple filter, low pass filter or band pass filter. And it is a drawback that every sensor that generally shows, but it is also more or less simple to delay it by applying the filter, hardware filter, but also digital filter with during the post-processing of the data sensor.
So any questions from our guests?
So you mentioned that you were using a piezo-resistive part inside.
Yes.
So
piezoresistive, yeah, generally the detective principle that I used a lot during my research here is a piezoresistive one, since the piezoresistive detecting principle has many disadvantages, since it presents a lot of drawbacks in terms of non-linearities of the behavior of the sensor, but on the contrary, it also shows most of the advantages, since it is simple to integrate with the soft robot, since it is simple the integration from both view of hardware and software. It requires a simple electronic circuit, and also we can apply simple model to compensate their non-linearities. So for this reason, generally I use the piezoresistive principle, but I also investigated different detecting principles such as piezoelectric and other. But the most promising from my point of view is the piezoresistive one.
Thank you.
So actually, I have two questions. One question is for Gionata and also you, Yixing, and another one is for Martina. Okay, so for Martina, you mean that you are design sensors, soft sensors. My question is that for soft sensors, and there are two ways. That one way is that model based to build model for soft materials, and the second one is that to do by using learning methods. And I want to know what's your comment for these two solutions.
Yes, both are promising. During my year, I used the model base to compensate the nonlinearity of the sensor, and it seems the most used model that we can use for the sensor, but also the learning base and is a method that we can explore, and of course it should be implemented for the soft sensor.
Okay, thank you. Okay, my second question is also about the soft material, because you also mentioned that the soft grippers. So my question is that have you ever considered the variable stiffness soft grippers? I think that will be more useful. And have you ever explored this direction? And also, what kind of difficulties or challenge in this direction?
Okay, so yeah, this is a good point. So to me, the reason why we are not using variable stiffness actuator, but we are using intrinsic compliance in the end is a safety reason. So with this structure, you are always sure that the interaction is somehow compliant. But it's really interesting to explore a way to change the stiffness of this finger. For instance, we are using a very simple structure where we have kind of rigid links and soft joints, and then we have a tendon-driven actuation. No? So if you want to have different closing trajectory, one thing you can play on is on the stiffness of each soft joint. For instance, if you have this joint very soft and these two more rigid, when you pull this close like this, if you have the similar stiffness when you pull it, you play like this. So for this gripper, you can change the stiffness. You can print different, it's a 3D printing process to make this, and you can change the infill density of your 3D printer. So you can make this joint stiffer or more compliant, and then you can select the trajectory. But it will be really nice to have something that can change the stiffness online. Now we are exploring some possible solution. One is to have a kind of a monolithic structure with certain shape, and we use one additional motor. Imagine that is a kind of spring that you can pre-compress, and basically you select the stiffness on this, and then you actuate with another motor. But for sure, it's I mean, it's something nice to explore, because the problem is this, no, that when you have to you are soft during the interaction, and it's okay. But then if you have to firmly grasp something, you want to be stiff.
You have
so you have to
have different stiffness at a different stage.
Yeah, so either you add like electromagnets or some other thing to add actuation, or with a variable stiffness soft actuator would be perfect.
I think that would be a perfect solution. Because for our human fingers, it is can have the variable stiffness, and when we explore something where we will be soft, but we want to push something and it will be harder or stiff or high stiffness. Yes. Okay.
Yeah, I also agree with Gionata. So it's definitely a good direction to explore. So when I did the experiment, the robot wasn't equipped with any soft sensors or tactile sensors. So at the beginning, we used the vision information, and I would also like to consider the comfort list of the users. So I used the force speed feedback from the robot controller. So we design a model and to detect this force resistance, and if this is detected, we enable the robot to automatically to optimize the dressing path, so that we want to improve the user's comfort list. Yeah. So that's how we solve that issue. But I would also say with more tactile sensors, or maybe the soft robotic grippers, it would be a better choice. Yeah, and it deserves a try. Yeah, thank you. So yeah. So is there any other else questions that you would like to ask each other? Okay. Yeah, thank you very much. I think we had a very good time chatting today. Yeah, okay. So ladies and gentlemen, as we draw to a close, I would like to express my sincerest gratitude to our distinguished guests for their invaluable insights and perspectives shared today. I would also like to express my sincere appreciation to our audience, both here in person and those joining us remotely. We hope to meet you again in the future. Goodbye.